Okay, DRL, this video is about the parametric study for TUALP simulation. So, okay, so first of all, we have designed flow conditions for each of you here. So each of you have a different flow conditions, and so for example, this is a parametric study, and in each parametric study, you first need to set up the simulation, and then you run the parametric study to change the tailpipe ID and signals. So for example, for the second simulation, you have a different liquid flow rate. Then you need to select a different pump. I will just use one example. So it is a tailpipe 1500 feet. It is here, and in this case, we are going to use okay, here. Let's do 1500 feet tailpipe length and 1000 GLR gas liquid ratio, and liquid production rate here 1250. So I'm going to run this parametric study. So first of all, you have a 1500 feet tailpipe, and then you have 1000 gas liquid ratio. So change your gas liquid ratio file here. If this is not the correct one, you just remove it and find the corresponding gas liquid property. So this is a PVT sim for 1000 gas liquid ratio, and the water part here you need to set up in the reservoir, and this is a water part for reservoir. So in the PVT sim file, we don't have water, and you need to set up in the Olga simulation. So we have first two settings, and the third one, liquid production rate 1250. So first of all, let's come here. First thing, we need to select ESP based on designed liquid flow rate, and the flow rate is 1250, and then we go to ESP, and we want this 1200. This number here represents the flow rate. You just select the pump with a flow rate close to your design flow rate, and we want TA 1200. So this is a pump curve for TA 1200, and in the simulation we want the ESP pump. We change it to TA 1200, and then the next step is to calculate ESP stages. I'm going to send you another file. So this is actually this is the final result, the final case, but it's TA 1200. So in order to calculate ESP stages, we need to roughly estimate the boosting pressure we need. So then we need to use this file. This is estimation for the pressure drop. We want in this case it's 9,800 and tubing diameter. This is all corresponding to your input. And this number here, I use rough estimation. You can just put something here because it's going to be different for each cases. But for example, this is 1,000. For this case, TRR is 1,000, and I use like 200 or 300. So for your case, you probably divided it by 3, like 1,000, and you can put the 300 here. And then this is a specific gravity and tubing head pressure, temperature. The liquid production rate here we want 1250. Now this is our pressure along the tubing, and then we need a 2,500 or 2,600 psi at the bottom hole. But according to our here, according to our input or downhole pressure, so this is early stage, is 1800, and let's just give you a brief example here. So early stage, if we assume early stage, then the pressure we need is this, and for late stage, okay, here. We have 1800, and then the EST. So for late stage, for that one, we have higher flow rate, and for this one, our flow, we have 1250, so our flow rate is kind of a little bit lower. We can assume some value, maybe 1500 or something. Right. So then we can make it 1200. So our required pressure or head for this study is around 800 to 1400. And another thing is, remember I had this assumption here. So if you assume a different gas liquid ratio, and then you have a different number here, right? So that's some uncertainty we need to estimate. We need to estimate the number, the head generated by ESD. So I can see, say for example, this is 100, and we have 3000. So let's give it a range. The range is from 800 to 1800. So we based on this number to select the pump stages. So let's go back to the TA 1200. We'll assume the flow rate is here, 1250, and then the boosting ability is around 5 psi. Uh, 5. And then this is a stage we need. So you see, we probably need around 200 and 300 to 300 stages. This is like a range, and the first thing for you to do is to tune these parameters to find the number of stages in this case. And so select the pump, and we already have a stage here. and we want the tailpipe ID 4" and 0.1 thickness. So it should be defaultly 4" and 0.1 inch. It is here, 0.1 inch. And the next step is calculate the reservoir pressure. So in this case, here this is after the tuning, I had something around 325 stages, but you can start with some numbers within this range. And remember, this is early stage, so this is probably not that correct. And this is more reasonable. For example, if you try a different number here, this is 280. So the second one is more reasonable, but you need to assume some number here. And in this case, I'll tell you originally I use 300, and then I tune it a little bit to find the best result. But after we got this number here, and we need to calculate the reservoir pressure. So if you remember, the reservoir equation here is a linear reservoir equation. It's pretty simple, right? And we have this is our production index, and this 0.6. So if we assume our bottom hole pressure is 1200, and our P reservoir. So our index is 0.6, and then our P reservoir the pressure difference is sulfur or flow rate. QL is 1250. So our pressure difference is and then our reservoir pressure. So our pressure difference is actually flow rate divided by index, and then our reservoir pressure is pressure difference plus bottom hole pressure. So this is our final number here. So you see our reservoir pressure is something around 3,800 or 3,300. So just put some number here, go back, reservoir, and put some number here. See here I use 3,050. And that's the reservoir pressure. And next thing is tune the reservoir pressure and ESP stages. So now we can run the simulation, just click run. Because this is going to take some time, I will show you some. I'll just show you some like a run setup. So I'll let you know how to tune these parameters. For example, if your stage number is too high, anyways, you may just use some crazy number. Yeah, if your stage number is too high, you've got this error number. And if your stage number is too low, probably have the same issue. It can happen during the calculation. Right now, I'm using some very extreme condition, so it's probably give you some error very quick, very fast. And I'm not going to continue run this case, but it's probably going to give you some error message after, like let's say several minutes, but once the simulation runs for several minutes. But once you have this error message, then you probably have a wrong pump stage number. So just tune it, increase it or decrease it. And another thing is once you finish your calculation, for example here. So for example here, you probably can. In this case, it is quite close to the design flow rate 550. But if your number is either too high or too low, let's see, your number may reach to 2,000 barrels per day, but your design flow rate is 2050. And then you need to do the calculation for reservoir pressure again, or just if you have a higher flow rate, then decrease your reservoir pressure. If you have a lower flow rate, just increase your pressure. I cannot show you the calculation process or the result takes some time. I don't want to waste a lot of time, but just imagine if you have a higher flow rate, you just simply decrease this number. Originally, when I run this example, I use 3,800, and the result gave me a flow rate around 1,500 barrel per day. That is higher than the desired flow rate. So and the difference is, for example, I just give you another. So I have, for example, in that case, my flow rate is 1,500, and my design flow rate is 1,250. So we have around 250 pressure difference, and we need a pressure drop to be around 400. And originally I set the pressure to 380, and I just tune it a little bit. I choose to use I choose to decrease to 300 psi because this number is around 400, and you also need to consider about the pressure loss in tubings and anything else. So I use some number here, just decrease it a little bit based on the calculation, and also I change the pump stages a little bit. This is my initial gas, 300 stages and 38 psi. This was my original case, and when I run the results, I got some. It's not close to the design flow rate, so I changed it to 3,500 and 325. And after the calculation, I got this result. And so this is like a Terran slack. This is perfect for this simulation. And once I got this result, I get this Terran slack, then I can set up parametric study. So for the parametric study, you have this you need to select tubing, right? And then you select all the pipe in the tubing, and you select diameter. Then also that you need to have first add a parametric study, and then you have two parameters, and first one is tailpipe tubing, and this is diameter, and the second one is in the library. You want to change the tailpipe tubing thickness, and here is the thickness. And this number here is in your project assignment. So here, you have the same same tailpipe size. That's all the similar. Under that, you just click run bench, and it will give you, let's see, just click here. It's going to run the parametric study for you. Yeah, here is parametric study. For example, this is a complete parametric study. Sorry, this is a complete parametric study. Sometimes, if at the beginning you have a very smooth pressure file, or I mean, if you don't have this Terence lag, for example, if you are that's just for example, if your pressure is something like this, you can try to decrease your pump stage a little bit, just to reproduce this Terence lag. Because when you have a very smooth line, you probably have a lot of more ESP stages, so that helps you to maintain the a more stable flow rate. But in our case, we want to we want to simulate the point of this study is to use tailpipe to eliminate the slack issue. So our first task is to find to generate a Terence lag, and then we use tailpipe to eliminate this problem. So if you have something like this, try to change the number of stages. Try to change it a little bit, and you may have a better. I mean, you may have a more clear slack result. And if you cannot, I mean, if you try several times, and it's always like a straight lines, or if you change the stage number, it gives you some errors, then that's fine. That means in this flow condition, it is there's no Terence lag. If that's the case, you just don't need to change it anymore. You directly go to parametric study, and that may give you let me show you an example. So that's another case. So let okay, yeah. Okay. That may, for example, in some case you may have a straight line for all the cases. That means that's fine. Like there's no Terence lag for these cases, but you can still compare the flow rate. For example, you can still compare the flow rate. There may still have a difference. You know, some conditions. For example, you have a larger size tailpipe. You still have this kind of unstable production rate. And that is due to some like pipe geometries. As for example, I will show you. For example, maybe you have some small gas bubbles trapped in some areas, and so that makes your production not very stable. And once you have a tailpipe, that's going to kind of help you to stabilize the flow. But if you have your tailpipe is too small, then you have the friction loss reduce the fraction rate. That's still something you can analyze in your report. But you may also, you may also have some result like tailpipe doesn't work at all. Like it's not going to help you reduce the slack flow, or it's always going to reduce your fraction rate. That's fine. You just analyze what you have. And in some condition, just like this one, you may not have a, you may not have a, for example, in this case, you only have a part of the line. That means you have first thing, you may have a wrong setup. Like in your case, your setup is not very good, and you have some errors in the parametric study calculation. But if you change some input settings and you still have this problem, then you may have other issues. Like you can analyze your settings, your results. Maybe you have your tailpipes kind of restricts too much flow, and it's not you have for example like this one, you have too much pressure loss, and that causes an error, which means this case is probably not going to work. But for like these two cases, I'm not sure. And like this, you probably still something like a slack issue. Once you have a pretty big slack, or you have some errors in the simulation, and that's going to stop your calculation. But anyway, just analyze the result. Try to complete your parametric study. And if there is no way to complete it, you always have some errors, and then just do some. You should analyze the reason for that. So that's something not. That's something can happen, and but it's not our goal of this project. We want to find something like this. You see, we have Terran slack, and we use a tailpipe, and tailpipe, for example, this tailpipe help reduce the Terran slack. And if we go to the production rate, similarly, you see with different tailpipe, different size of tailpipe. Firstly, it cannot help us to stabilize the flow, but at some point, the flow is stabilized. But if we further use a smaller pipe, you see we have we reduce the flow reduce the flow due to the friction loss, and that is intake pump intake liquid hold up. You see, at this for this case, we have a more smooth or more stable liquid hold up at pump intake, and that can help us to reduce damage to the pump. Although we have a separator before ESP, but once you have this Terran slack, the separator may not work 100% efficient. If there is gas bubbles in the pump, that may cause other problems. So we are trying to reduce like this point, like this big gas pocket. We also here is the accumulated production rate. As you can see here, still here, with this tailpipe, this tailpipe is 1.38 inch, and we have the most or highest accumulated production rate, and that's all can be included in your report. So, for example, here, whether this simulation has Terran slack, yes or no, and pressure drop of tailpipe. So that's something here. Once you plot, you select the data. That's for the wheel bore, and that's for tailpipe, right? And you can copy the data, and just plot it in Excel, right? And then you can do calculations. For example, and So that's a tailpipe outlet. Sorry. Yeah, that's a tailpipe outlet. I'm just going to use an example, so I will delete all this. So case one, tailpipe outlet. Case one, tailpipe inlet. So I will just delete all the rest. And tailpipe one, and this is this is for example, tailpipe, outlet, inlet, and you can do calculation. Right, and that's a pressure drop across a tailpipe. That's for the first one. That's this one. This may not be a very good. I'll do it again for the calculation part. Tailpipe tubing. Okay, that's the wellbore. So this one is DP from wellbore to tailpipe. One is from this is tailpipe, DP for tailpipe. Just to give you two examples. So, for example, this is a total pressure drop from bottom of reservoir, bottom of like end of the wellbore to the tailpipe outlet. And this is the pressure drop of the tailpipe. This is for the second case. Example. This is this one is case one, and this one is case two. The pressure drop from bottom of the wellbore to the tailpipe outlet, and this one is pressure drop of the tailpipe. Okay, so that's something. And in the Excel, in your in here, you can just put the mean number, like mean value. That's the so the pressure drop for case two is around 500 psi. For case one is around 2000 psi. Just get this number from the calculation and put it here. Let's see, for example, 2500. And that's also 2500. And the QL at ESP outlet, that's something here. Similarly, just use the average number. that's about 1250, right? So it's close to our design flow, 1250. And surface gas liquid ratio. Well, that's something we want to do the calculation. For example, in the tubing, you can do the calculation in Excel, or you can just estimate in the Olga. Let's say we want the surface at the surface condition, and change the unit. You see, this is a result for case 1, and the liquid flow rate is around 700. Gas flow rate is 4.5, and that is something like that, like 570. But let's say for a different case. Okay, I got it wrong. Sorry. So we need to consider the gas flow rate in the tubing and also in the annular. So here is the annular gas flow rate, outlet. Okay. So there should be no liquid in the annulars, but there should be gas flow in the annulars, and we just plot gas. Okay. So that is wrong. I'm just going to show this example for the case 2. So we have so first of all, we have 2 gas flow rates. One is 5 to 10 to 5. Another is negative, but this negative is because of the direction. If you take a look at the direction, right? This is annular direction. When it is negative, it means like producing. Negative is in the opposite direction. So that's like that will be 10 to 6 plus 10 to 5, right? Gas flow rate and liquid flow rate is around like probably something like 1100. So you see, that's 1000 GLR, or designed or designed gas liquid ratio is 1000. So that's very close to our design point. Okay, so that's something. It's a little bit different here. We want the outlet. Here we want the surface. So here surface QL is 1100 cumulative liquid production. You can find in this plot. Let's see, 900, something like that. This is an example of how I build this this table. And you can also, in your report, you can copy some image, and just plot it in your report. Just to help you to do some analysis. Okay, that's all for the parametric study. And let me know if you have any questions. So just send me an email or